Hello, everyone. It's kind of weird that I'm using a mic. With everyone can hear me, but we're gonna use it for the people on Zoom. So I want to thank everyone coming out today. We're here with Terrapin Rockets team. So we're a club on campus that we launch rockets. It's kind of the name, but we do a lot of software stuff. So we thought we'd come by, give a talk on embedded software, which is something that you maybe have been introduced before to a little bit, whether in high school or some of your intro classes or not. Maybe you don't have any experience, and we'd love to give just an introduction to embedded systems with a focus on like the programming side, embedded systems programming. It's a hackathon or a tech conference. So yeah, we thought that would be a good introduction, a good topic to talk about. Cool. So we're going to cover a little bit of things today. First, we're just going to talk about what is an embedded system, keep it at the very basic level. How do they work? What do they do? What are some examples of some of them? Then we're going to look at the introduction to the basic hardware involved with some embedded systems and the software. We'll introduce kind of the Arduino framework, which is kind of the building block you can start at, really introductory level, really help you get going with that. Then we'll do a demo with the Arduino framework so you can actually get writing code. So if you have a computer, you'll be able to follow along with that. And then finally, we'll talk about some things moving forward, how you can use more advanced hardware or do more stuff with software and really take it to the next level. And we'll go through like a little case study of what we do on the Rocket team sometimes. So first question, naturally, what is an embedded system? I like to think of an embedded system as kind of a pairing of hardware and software to do a very specific task. So at the most basic level, at the most general level, you have your computers, your laptops. These are very generalized things that can do a whole range of tasks. Embedded systems are specialized software and hardware that kind of take some kind of input, do some very specific task, and give you some kind of output. So some of these inputs can be something like a sensor reading or user input, and some of the outputs could be as simple as just a screen that you shows a couple numbers, or it could be actuating stuff. It can be doing stuff on a rocket. It could be doing stuff. Your phone is an example of a very complicated embedded system, things like that. So I want to talk about what are some examples of embedded systems. If anyone wants to talk and give some examples, you're more than happy to. Anyone? Any examples that you know of an embedded system? There's a lot around us right now. Yes. Yeah, so someone said in the audience that the hardware behind the phone, that's a great example. Phones are actually really cool because they really blur the line between what is an embedded system versus like what is a computer. There's not this really hard definition. Your phone has a lot of computer components to it. You can go online, you can do all these different things. Then your phone also has like an inertial measurement unit and a GPS in it that like kind of it can figure out where it is in space and how it does all this motion stuff. So in that sense, it's more of an embedded system because it's taking these sensor readings and doing some now them to give the user some output information. But here's some examples that I thought of. First thing that comes to mind for me, rockets. There's so much software that goes into them and all the actuating and moving, the thrust vector controlling and all the grid fin steering, all this stuff, all these complicated things all happen because of embedded systems. But then there's something as simple as like a blood pressure monitor. So basically this thing can strap onto you. It really has probably one sensor. I don't know what it does, but it reads somehow your blood pressure and your heart rate. And it kind of just gives it to you in that very simple format. And there's a couple other things. So some major ones that happen in industry a lot are robotic arms, and that can encompass more to like manufacturing capabilities. So if you look at a factory line, everything you see there that's automated is all running on embedded systems. They don't have these full-scale computers controlling them. It's these very specialized things that go in there and actually get individually programmed to do the exact task that they're supposed to do. So now let's get into a little bit of the basic hardware. And I realized actually I didn't introduce myself at the beginning of this. So sorry. My name's Michael. I'm a junior aerospace student. I'm actually here with two other presenters on the Rocket team. One is Varun, who's going to be speaking next. He's a sophomore CS and aero student. And then we have Avi here too, who's a CS student. So I'm going to hand it over to Varun to talk a little bit about the hardware behind embedded systems.
Yeah, so I'm Varun. I don't know if this thing works. I'm Varun. I'm a sophomore aerospace and CS student. And so I'll talk about a little bit the hardware involved. And so when you're dealing with embedded systems, there's kind of a direct pipeline in which you can connect different components and have this data flow. So embedded systems usually start off with a sensor of some kind, whether it be an array of sensors or a single one, whose job is primarily to obtain data and then relay that to the microcontroller, which you can think of as kind of like the mini computer or the brains behind the operation. So this microcontroller will kind of deal with and process this data, perform some sort of operations, and then feed this output to the output devices. Now, for some cases, if you're just trying to record data, this can be something like an SD card. Or in other cases, like Michael was saying, if you're trying to control a robotic arm, this can be the actuators or the motors, which are going to move the joints of the robot. And in between all these different parts, you have what are called GPIO pins, or general purpose input/output pins. And these are essentially ways that the microcontroller is able to receive and relay information between the sensors and output devices. So just kind of the interface which you deal with. And here we have examples. On the left is an altimeter. So it just reads height data and how high you are in the air. So that's an example of a sensor that we use on rockets to take in information. And the output can be an SD card, for example, if you're just trying to store that data somewhere.
Yeah, so now I'll talk a little bit about the software that goes into embedded systems. So when most of you write code, you probably do it in a language like Python or JavaScript, but embedded systems is a little bit different. The languages we use there are close to hardware, so things like C and C++, and even Rust. And we like these because they're super low level language, and they allow us to optimize memory usage. If any of you guys have taken CMSC 216, you know how annoying it was to allocate memory, but when done right, it allows us to be highly efficient. And another advantage a language like C gives us over something like Python is Python's an interpreted language, but C compiles directly to machine code, which we can then just upload onto an embedded system and run. And we also have a few controller-specific languages, like one for Arduinos.
Yeah, so a popular use case of embedded systems that a lot of people deal with are Arduinos, simply because they're easy to use and provide an existing framework. And so the Arduino language is one that's built on the framework of C++. And so depending on which flavor you use, pure C++ code may work on the Arduino. And not only that, but the Arduino as a whole has cheap and easy to use boards, which is why it's widely available and widely used. In terms of the Arduino IDE, you can download that, or you can host it on different applications, such as having VS Code extensions or different IDEs in order to run and write this code. And as for how the actual code is set up, you have two main parts. You have a setup part of it and then a loop part of it. And so the setup function is essentially what's run on startup. As soon as the Arduino receives power, what are the initial operations we need to perform in order to initialize and set it up for performance? And then loop is essentially a function that is consistently called over and over again that defines the behavior that you want the Arduino to listen to and perform when operating. And so those are the two main functions where you'd write the code for the actual Arduino. Now on the hardware side of things, I know before I mentioned GPIO pins and stuff like that. And so the way you connect the Arduino to your computer in the first place is via a USB port. Then the Arduino will have a USB to serial chip, which is essentially how it interprets the data that your computer feeds to it in order to process code and upload that code onto its systems. Then when you're dealing with the Arduino in an actual application, it uses those GPIO pins or digital and analog pins in order to obtain data as well as give out data to the inputs and outputs to the system. The differences between digital and analog pins is that digital pins only have two possible values, and that they can either be high or low, versus analog pins, you can write a variety of different values based on the voltages that you give out. So these are all components that have both software and physical applications. And then finally, you have things like the 5V/3.3V pin, which is just where you power the Arduino, as well as the main microcontroller within the Arduino, which is what performs the operations. And you can think of as kind of like the CPU.
Yeah, so now I'll go a little bit more in depth into the Arduino software. So as Rune just mentioned, we have a setup and a loop function. Setup just runs once when you run the code. Loop just runs continuously, and kind of think of it as like a while true statement. So in the setup function, you can see we have a function called pin mode, and we pass in 3. That's just a pin number. And then we can pass in either input or output to designate it as an input pin or an output pin. Then we also have something called the serial. You can think of the serial as kind of like the console in Java, where you can print stuff to that and see data. As you can see, we print setup done to the serial. Then in the loop, we have a function digital write. This is writing to a digital pin, and we pass in the pin number and then the value, high or low. There's also an analogous function called analog write, where you can pass in similar values. Now you can see on the top left, we have a verify/upload button that you just use to check if your code doesn't have any errors, and then actually use that to push it to the Arduino. And then on the top right, we have the serial monitor, which again is just a console. You can click on that, get a view of what's happening.
Cool. So that was probably, I know the first time I learned about Arduino, it was very, it was thrown all at me. And I was like, I have no idea how to apply this. There was so much information. How do I do this? So I think it would be very useful for us to go through a little demo, making a really simple circuit, but I'll explain how this simple circuit is very you can use it for a wide range of applications. So this is the circuit we're gonna be making. Don't think you have to memorize this. I'm gonna go step by step on how to make it. But at a high level, there's really three components to the circuit. You have your input stuff, your input sensor, and that's kind of in the top left, that little knob that's there. That's called a potentiometer. All that is if you've heard of a resistor before, it's just a variable resistor. As you change that knob, it actually changes the resistance that's kind of felt by the current going through the wire, is a way to think about it. And the reason I chose to use a potentiometer for this one is most sensors in almost every application are actually just potentiometers at heart. So for example, if you have something that measures acceleration on a chip, that's actually a spring that's on the inside that when it compresses, it actually increases the resistance of a predetermined circuit on that acceleration chip. And that just gets interpreted as some acceleration by predefined notions because they know what the voltage and current going through is. All that to say, we're not just turning a knob for no reason. That's actually how real sensors works. And that's kind of why we're using it in this example as a simple model of a sensor. Then we have all these wires that run into the Arduino, and we'll get into each one of those. And the Arduino is just going to be performing a simple task. It's reading an analog in from the potentiometer, and these ranges range from, it's based on voltage, but it'll range from 0 to 1023. And basically we're gonna do some action on that and then light up the LEDs based on what we want to do. So what I have this set up for now is it's gonna do, if it reads over 250, it's gonna output the green light. If it's over between 500 and 750, it'll be the yellow light. And if it's between 750 and up, it'll be the red light. So super simple circuit. You can imagine how we're outputting these signals that can be going to something that's a visual thing that's happening, or it could be actuating a motor, all that. But for the basics, we're just going to deal with this. Yeah, and this is what the code's going to look like. I guess I probably should have this up here when I was talking about the code part. Either way, we're going to go through and do this together. So if you want to follow along with us, you can go open your laptops and go to a website called Tinkercad. So that image that I just showed you is from the website, and I'll give you time to get on it. You probably have to log in with Google to make an account if you want to. It's super simple though. They're not going to send you a million emails, so don't worry about that. But let me just delete all this. Well, I'll keep those components out there actually. So yeah, we're going to go through and build this circuit. So the first thing we do is, you guys are getting on to Tinkercad, take your time. You'll be able to catch up with what I'm doing very quickly. But yeah, I guess I'll wait for you guys in the audience. If you're getting set up, just give me a thumbs up if you get there. I don't know what that line is. Okay, so let's get started. Really the first thing we're gonna do is we're gonna pop out our Arduino, and the circuit we're gonna make is on the right there. So you can follow along and kind of know where we're going and go a little faster if you know what you're doing. The next component we're gonna need is called a breadboard. This is really just to hold everything together, have all the wires connect to each other. It's if you would actually make the circuit in a commercial application, this thing would be abstracted and not there, and the wires would just actually connect together. But all it does, if you see how I'm highlighting this, everything that's highlighted in green is connected underneath the breadboard by a wire, so that they're all electrically connected. So plugging in something here would be connected to something here. So these rails are all vertical, these rails are all horizontal. It's not really crucial to know how they work for this application. So first thing we do is we're gonna actually, you probably can't see that. So we can take potentiometer over here to bring up what we need. And this is got by, oh, I don't know what I did there, but yeah. You can just drag that over to somewhere on your thing. The next thing we're going to need is, actually, let's plug this in first. So common convention says we want to plug black wire, the ground side of it, into using black wires. So I just changed the color to black for that. The wire color actually does not matter at all. But if you make really more complicated circuits, it gets hard to see and read. The next thing we're going to do is we're going to plug in the third pin, that complete other side, down to this 5-volt pin here. So what we're going to be doing is we're taking, right now, we're throwing 5 volts across this potentiometer, this variable resistor. And then we're going to need a way to read the change in resistance. We change the resistance by turning this knob, but we need a way to read that. So we're going to take a blue pen, the middle one, and we're going to send that to A0, which is our analog 0 pin, which again can read values. It can read different voltages and output a digital value for that voltage between 0 and 1023. The next thing we're going to set up is, let's quick connect the ground between the Arduino and the thing. So I think this one's ground right here. Just connect that to the black rail. Just a thing to make the circuit look easier to run. And then we can go grab our LEDs to put on. And there's resistors on the one on the right, but you actually don't need resistors in Tinkercad for 2 reasons. One, it's not a real circuit, nothing's going to blow up. 2, it's the Arduino does not produce enough current that it actually is going to do damage to any real LED. But most of the time in most applications, if you're using LEDs, please use resistors, or else you're going to burn out your LED. So just changing the color of these. And it doesn't actually matter which pins you hook these up to, because you can just change the pins in the code. But for the code that I wrote, we're going to hook it up to pins. I think green is on 5, and then yellow is on 4, and then red is on 3. Oh, sorry. And I'm actually hooking up the wrong side of it. Let me go back and change that. So you want to hook up the right side of the LED, which is the anode, to the positive end. And the positive is what's kind of coming out of the Arduino. You can think of it that way. And then it's all going to be grounded at the same spot. So yep, just like that. And if I'm going too fast, please let me know, anyone. But cool. So now we have our circuit set up. It looks significantly more ugly than the one I made on the right, simply because it's really hard to make a circuit when I'm looking and presenting at the same time, surprisingly so. Yeah, let's write the code for this. This is what we're here for. Tinkercad is very useful for anyone, all ages. So the first thing actually comes out is blocks. We're not going to use blocks. We're in college. We can do it. So yeah, it's going to be hard for me to type with this, but we're going to figure it out. Let's delete everything already in here. We don't need that. Actually, I'm going to keep it because I don't have everything memorized, but we can get rid of this. So first things we wanted to find at the top is, let's do a green LED and I guess our pins. And I'm writing way less because I don't want to deal. Actually, we'll write it specifically. So let's define the pin numbers for all of them. Remember, we put green on 5, and then we put yellow on 3. Oh my lord, this is so difficult. Yeah, actually. So yeah, Varun's gonna type for me because I'm struggling with the one-handed typing. So we have our LED green on 5, LED yellow on 4, and then we have LED red on 3 right now. And then we're gonna set our pot pin. So you just see POT_pin and set that to A0. I realize now that this is C++ and it should be typed. So can you make them all ints for me? Yeah. Just like that. Yep. And then we want to do a few things. The first things we need to do now is we need to set the pin mode of each one of these. Well, some to an output, some to an input. We have to set all of the LED pins to an output. The reason we're doing that is because we're actually going to be doing some computation on the thing and then sending it out. So we can do pin mode and then LED green and then in all caps output. And that's kind of some Arduino specific words. Output in all caps, input, high, low, they're all defined in the Arduino framework. Yeah. So we can set all those LEDs to output, and we can set the PRT pin, which is the potentiometer, to an input pin. I'll give Ruben a second to do that. And we can set that to input. Yep. And the last thing we want to do in the setup function is we're going to want to call serial.begin, which just sets our serial monitor. So we'll be able to see kind of the value we're reading in on the potentiometer. And we're going to do 9006. That's just how fast it reads in the bytes, I think. Yeah. So now we're going to go to the loop function. And what's the time we're looking like? We're running a little bit late on time. So if Varun goes to the other Arduino, just clicks on the other Arduino real quick. The code's actually written there. So you can just copy and paste the whole thing, but it looks very similar. I think I named the LEDs a little different, so you're gonna have to update that. But yeah, we can go through the code once he gets it back over and is updating the LEDs to the right names. But all this code's doing is these first two lines is we're initializing this variable value to analog read what the power pin is getting. So I've been talking a lot about reading 0 to 1023. Value is just going to get set to whatever it's reading on that, and it's just reading a voltage. And then we're just going to print to the serial monitor what that value is, so we can make sure that the logic's working. And then our logic really is just if it's over 250, under 500, which is basically it's going to be reading a voltage of around, probably if it's 5 volts, 0.25 times 5 volts to half of 5 volts, 2.5. And then the next step, we're going to put it yellow, the next step red. I guess if you want an application for this, it's kind of like if you're reading something and you don't want it to be a like in a manufacturing setting, if you have this variable you care about, like let's say you care about the pressure in a tank, it's fine when it's under 500, and then it gets to kind of a warning range, then like an error range, and you should probably leave where you are because that tank's going to blow up. But if we go hit start simulation in the top right, it will actually run the code, and if we wrote it right, it won't do anything. And then we can move that, and it will hopefully. Can you open the serial monitor actually on the bottom left? Yeah, so it's reading 0, which is what we think, because it's 0, and as he turns it up, reads higher values. You can barely see the green turn on, the yellow turn on, but I can confirm they actually are turning on. We have a little setup here where we actually made the physical version of that. So if you want to play around with it, you can. I don't know. It's a fun knob to spin. But yeah, that's the little demo we have. I hope if you've never used Arduino, this is a good introduction to help you like not be terrified by it. I just remember my first time. I see all these pins and I'm like, what is a pin? What is a voltage? Like, I'm scared. But yeah. So yeah. We pull this presentation up. Thank you, Varun. Absolute goat for writing for me. I was struggling hard. Cool. So yeah, let's talk about some moving forward, how you can go forward with embedded systems and what kind of the stuff. Arduino is very basic. How do you take this into industry? How do they do it? And what are some steps if you understand what's happening, how you can go forward and learn some more stuff. So I'm going to hand it over to Avi for that.
Yeah, so first I wanted to talk about something called real-time operating systems. Now, the typical operating system on your computer is actually not a real-time operating system, but the importance of this is when we need something done at very specific times. And a good example of this is landing on the moon. We need things to happen in a very specific sequence at very specific times. And your computer operating system doesn't exactly do that. Like there's a little bit of leeway there, right? And an example of this is a Raspberry Pi. It can actually run a real-time operating system. And this is kind of like a step up from an Arduino. An Arduino uses something called a microcontroller, which essentially just runs one script at a time. Like we can only run one thing. But on something like a Raspberry Pi or even your computer, you can run multiple different things at once, as I'm sure you've noticed. Next, we have field programmable gate arrays, or FPGAs. These are essentially just programmable hardware, and they're just used for applications where we need maximum performance. It's just a little bit more efficient than just pure software. And since the name of the game in embedded systems is efficiency, it's good for us.
Cool. So in these last 5 minutes, I want to spend a little bit of time talking about how we actually apply this to the rocket stream and hopefully recruit some people. Because why not? If you think this is really interesting, the rocket team, we have so many roles for software people to help out and to develop stuff and develop their own skills and take really ownership of a project and see it all the way through. If you're looking for experience, we're always open. But something that we really do work on and kind of taking it one step forward, still working within the Arduino framework though, is what we have on our rocket, which is the air brake module. So kind of the goal of the rocket that we make for a competition is to reach 10,000 feet as close as possible. You don't want to go over, you don't want to go under. So what we do, we overshoot it, and then we can control the flap angles at one part, increase the drag, and kind of bring our altitude down until we're at 10,000 exactly. It's a very simple algorithm. It's actually a very complicated algorithm, but simply what it does is it reads the state of the rocket. So we have two sensors, an accelerometer, which reads our acceleration, and then a barometer, which reads our height above the ground. We use this data. You can integrate it. You can do all this stuff. That fancy term is an uncentered Kalman filter that we use, but you don't need to know that. It basically just integrates it and uses a math model to figure out what our apogee is, and then tells another controller what angle to use to deploy a motor's flap angle at. So it's a very complicated system, but all it does at a very simple level, and there's an image of it on the right, is the computer, I guess, that we made, is those two sensors, as I said. They all feed into what we have there is called a Teensy, which is just like a more memory, faster Arduino, but same concept. And it reads that in, tells it to deploy to a flap angle, and kind of brings it down, brings altitude down until it's at a good spot. So if this seems interesting to you, we do a lot of things similar. This is just one of the sub teams that uses software. We have an avionics team, we have a payload team, all that uses software. But with that, I guess I'll open it up for a few questions if you have any. We'll be around to talk if anyone's interested. But really, thank you so much for coming. This was a lot of fun for us. We've never presented here before. And yeah, thank you. Were there any questions? I kind of ended that. Oh yeah, we can actually pull out the demo. It's kind of hard to see because we plugged into a computer, but yeah, so
Just spin the knob.
you can just spin the knob. Yeah, it's kind of at a middle spot right now, but for everyone online, we're spinning the knob and it's changing the light just like it did online. Yeah. But yeah. Is anyone online? Oh, we have a question. Yeah. Yeah, so we had a question which was what kind of competition do we compete in? And what we compete in is the Spaceport America Cup, which is the largest intercollegiate rocketry competition in the world. About 120 schools from all around the world fly out to New Mexico. We all launch rockets up to 10,000 to 30,000 feet. Whoever gets closest wins. Last year we got second place in our division. Super cool. So if you want to be on a winning team, that's us. Yeah, great question. If anyone online has any questions, feel free to drop it in the chat or unmute if you have that ability. I don't know. Cool. Well, if there's no more questions, thank you all so much. Really appreciate you guys coming out. Cool.